Welcome to next segment of our podcast. Thanks to Euripides for joining us. This is Euripides Kantzas. He's our leading expert in numerical issues and carbon cycle modelling. And Euripides has been leading our kind of integrated Earth system weathering simulations. So you were involved, weren't you, Euripides, right from that position paper that we were talking about with Mike earlier in 2018?
Yes.
Doing the simulations for that.
Yeah, so I was working with Mark Lomas in the maths department back then, and you started the center, but I think at some point you realized, okay, you need some other people beyond geochemists. So you came over, you spoke to Sean Quigan and said, you know, I need
Who have you got, man?
What do you got? We need some number guys over here. So I came over, Mark took over the geochemistry modeling, and I took over the data.
Yeah, I remember we went to coffee.
Yeah.
I felt like I was being interviewed. I'm not interviewing Euripides. Does he want to come and work with me?
I was doing different things back then. I was doing fires. I was working at how snow melts in the Arctic. It was
all this boring stuff. Yeah.
So in the center, what I do is obviously geochemists look at how much weathering we get, and they look at the field or mesocosm experiments. What I do is I write this big data simulation optimization models that try to figure out, can you scale it? Can it actually happen in the real world? How much it's going to cost? Which countries can do it? And a big aspect of it is we have to do this into the future. So we're not looking at now, because it's not going to happen in the next couple of years.
It's going to take a couple of decades to spin up if it takes off. Yeah.
Yeah, just to open the quarry takes 10 to 20 years just to get the permits going.
If you need a quarry.
Yeah.
But I think one of your first contributions was to that 2018 Nature Plant paper. And I think when you did the simulations, you were the one that really showed actually if you do enhanced weathering on agricultural land, the big winners are going to be USA, China, and India.
Yeah.
And that message still holds true today. The three countries that could contribute most to CDR with enhanced weathering are China, India, and the US. And those are the three biggest emitters. So there's almost this kind of moral imperative for these countries to do something about it.
They're big countries. They have croplands. They have basaltic deposits close by, because that's important as well. If your basalt is 200, 300, 400 miles away, the cost is going to be very big. And what you also need is you need a sort of industrialized country. You need a country that has the road networks, rail networks. It needs the electricity capacity to grind the basalt. It needs the machinery. It needs the trucks to move it around. It needs an advanced agricultural sector that can spread so much basalt.
Yeah, I mean, that's a very good point, because I think one of the points when we built the centre, which I didn't mention earlier, was that we did bring in people that are involved in macroeconomics. So we had Neil Edwards at the OU, JF, Jean-Francois Mercure, Exeter, and Hector Pollitt. And one of the things that we have been, pioneering, is that the right word? Is and that you've developed really is this integration across enhanced weathering models with macroeconomic models, thanks to Hector's, JF's, and Neil's input. And that's allowed us to understand costs of CDR, which is crucial.
Yeah, I remember when I was doing it, I was doing the optimization, and I was asking, okay, what's the best way to maximize carbon sequestration? And the optimization, I didn't have the costing yet. So the optimization would just say, if you move this basalt 1,000 miles, you can get 2 grams of CO2. And I'm like, oh, that's great. And then when I did the cost, when I calculated the cost, the graph didn't have enough length on the y-axis because the costs were $20,000 per ton of CO2. So then I realized, okay, we need to get the cost as a constraint in the optimization, and that's how we do it.
Can you tell people what for people that aren't favor this? What do you mean by optimization? Can you unpack that?
So So in optimization, usually is you say, okay, what's the optimal height of this bridge, and it's 23.29 meters.
In terms of what structural integrity
Yeah,
versus
in terms of height, for example.
Yeah.
But this optimization it's not what we want, because what we want is what is called a binary optimization. So it's like you don't ask how long it is, but you ask yes or no. If you're a company, for example, and this is where it comes from, this type of optimization. If you are a company, you have 20 factories around the world, and you say what's the optimal way to make money, you need to know if you should open or close that factory. So you need those zeros and one there. You need this binary decision. And when we run this optimization on the basalt, we need to know which quarry should provide basalt to which grid zone, based on usually how far they are. So you have 20 quarries, you have 5 million hectares of croplands, and you need to know which one should pair with which. And so this is a specific, it's kind of a niche type of optimization, but this is what we need. And what goes into it, it goes the distances to the quarries, it goes how much will it cost. There are other things like the electrification of the transport network. That's also a big uncertainty, because as I said, we do this into the future. We don't do it now. We're looking at 20 up to 80, 100 years ahead.
But I think bringing the quarries into it was good, because I think when we wrote the 2020 paper, it was like, there's plenty of rock, don't worry about that. And then one of the kind of innovative things that you did was realise actually rock is a finite resource and it has to be produced, and you have to figure out, if you want to apply 40 tonnes per hectare to this much farmland, are the quarries going to be able to provide it, and what's the production rate, production relative to demand relative to supply, I suppose. And you developed a whole set of sort of demand supply curves for different quarries to constrain our analyses, particularly in the US.
Yeah, because, I didn't know, I'm not an expert in mining or quarry production, but I remember I was reading back then, I was reading a machine learning book, and it was talking about neural networks and how they use a logistic curve to classify. And I remember I saw the shape of the curve slowly increasing and then flattening out. I thought, why not? We can use this as a proxy to how a quarry develops its production to the years.
So that's your bedtime reading, machine learning books.
I watch a bit of TikTok as well. But that's how. So it's always when I came into this group, I didn't have a background in data or machine learning. So it was one of the things that I started doing, and I still do it now.
But maybe we should just, we'll close the segment by just saying you've got, secret project under wraps, but it's not very secret if we talk about it now. But there is a global emulator in the works, isn't it? AI-powered global emulator.
Yes, we're trying to do that because, so the model we have, the weathering model that we have, it was developed, and when Mark Lohmans was testing it, and he's testing it, he's always testing it for like 2-3 years run. So he does a run for the next 3 years. When we do these models, we run them for 50. So it takes a really long time to run it. It could take 2 weeks to get a result for a single country. So as I was working on it, I thought, we have neural networks that can approximate time series. And basically, there are neural networks that you give it, for example, a time series of atmospheric temperature, and it tells you what it's going to be tomorrow. So the data that comes into the weather model are time series. It produces time series, and I thought, okay, instead of data, we can just try to feed these data into the emulator, into a neural network, and try to predict what the model would tell us. It's basically a model of a model, which runs
fractions of a second.
Fractions of a second, yeah.
So you can do global simulations in 10 seconds rather than even 20 years.
Yeah, you can.
Yeah.
So this is what we have developed it for Australia, for a study in Australia. as a test bed, and now we're going to do it for the world.
Now we're going global, to be downloaded for anyone, really.
Yeah, maybe deployed online.
Yeah, and deployed online. So that's great. Thanks very much, Euripides, for joining us. It's been great to chat with you.
Thanks.